This is our CE 461 semester modeling optimization project. Our group consists of Daniel Penn, David Schoonover, Mark Selinsky, and Dennis Dubchek. This project's aim was to design and improve a work cycle done on site at the University of Alabama. The site encompassed the building of 4 sorority houses and had a unique layout. The work cycle consisted of excavation, hauling, and stockpiling for contingent backfill. Our project consists of the construction of 4 new sorority houses located to the east of Bryant-Denny Stadium to the south of the President's Mansion. We'll be looking at the excavation and hauling of soil from lot number 3. 80% of the soil will be hauled off the site and 20% of the soil will be stockpiled on site and used for backfilling on lot number 1.
As Mark explained, the project consisted of 3 activities. Number 1, excavation of the basement. Number 2, hauling of the dirt. And number 3, stockpiling of the dirt. And as far as stockpiling goes, 20% of the dirt was to be stockpiled on site, and 80% was to be stockpiled in a contractor's stockyard, was to be hauled with several constraints. As far as on-site equipment goes, the construction team appropriately sized the amount of work to be done with the proper machinery from prior working knowledge. The equipment to be used was number 1, excavator. It was a track hoe. It was model Komatsu PC228US-LC. The dozer was a Cat D5N XL, and the truck was an 18 cubic yard dump truck. When considering cost of the equipment, we cross-referenced with Means Estimating Guide, online estimates, and textbook examples. When we discussed this with our site manager, he verified the accuracy of our values.
When considering validating our model, first we figured out what our baseline formulation would consist of. We figured that we'd need 2 18 cubic yard dump trucks, 1 track hoe excavator, and a dozer. We based these values upon our time constraints that we listed for each activity. For the track hoe and the dozer's highly repetitive activity, we modeled it as a normal distribution of times, since all of the means were similar to each other. When it came to the truck, who had lengthy activities that were far apart in duration and highly variable, we felt a triangular distribution was more appropriate to put into our model. When creating our model, we began here with the track hoe's repetitive activities of excavating and hauling away. We came here to this fork where, as mentioned earlier by Daniel, 20% of the material was stockpiled on site to be used for the dozer. We modeled this as a probability situation upon 20% of the time dirt would be hauled this way. The other 80% was hauled via the dump truck through the construction entrance with the truck weight, and this was a narrow construction entrance that we modeled to where only 1 truck could go through at a time, either entering or exiting the site. After this, the truck immediately pulled into oncoming traffic where a traffic controller was needed to direct. After this, there was roughly a 5-minute haul to the contractor's dump site where the material was stockpiled and the truck returned empty back to repeat the activities.
After validating our baseline, we performed a sensitive analysis in order to improve the production rate and optimize cost. This table summarizes all the scenarios that we included in our sensitive analysis. Before making our final recommendations, we took a look at the contractor's situations to figure out which factor of construction was in highest need for improving. In this case, it was decided that the optimization was beneficial for reducing costs due to high amount of slack activities. We ended up adding 3 trucks to the baseline, which increased the production rate by 150% and ended with 1,267 cubic yards per day. It also lowered our cost by 31%, and it came down to $4.42 per cubic yard. Thank you. This is the end of our presentation.